Okay, hi everyone, I'm Katie,
And I'm Ziyan.
and we are going to be teaching you about acetal formation. So, acetals are formed when a ketone or an aldehyde reacts with an alcohol in excess, so at least two equivalents of an alcohol. The reaction can be acid or base catalyzed. However, if it's base catalyzed, it won't proceed to form the acetal. It'll only form the hemiacetal intermediate, which can be seen on screen. The hemiacetal intermediate has one alcohol substituent and one ether substituent. However, if the reaction is acid catalyzed, you can proceed all the way to the acetal product, which has two ether substituents. So we are going to be showing the acid catalyzed mechanism for this reaction, so it'll proceed all the way to form the acetal. The first step is the protonation of the carbonyl oxygen on the ketone. And then the second step is the nucleophilic attack of the alcohol onto the ketone. Sorry, our tablet is lagging. So then once the alcohol attacks the ketone, the double bond will flip up, forming a tetrahedral molecule. And then the conjugate base of your acid catalyst will deprotonate that alcohol that just attacked, forming the hemiacetal intermediate. Wow, okay. This keyboard's being really weird. This is the hemiacetal intermediate. And then, since we're doing the acid catalyzed mechanism, next we will protonate the oxygen that used to be the carbonyl oxygen to form the oxonium ion, which is a really strong leaving group. After that leaving group will leave, forming a carbocation. And then with that carbocation, the second equivalent of our alcohol will attack, forming another tetrahedral molecule. And then finally, the conjugate base of the acid catalyst will once again deprotonate that alcohol that just attacked, forming our acetal product. This reaction is also reversible. As you can see, we use the reversible arrows to draw it, meaning that if you have your acetal product and you add an acid catalyst and water, it will react with the water to then reform the ketone and the two equivalents of the alcohol that were the original reactants of the original reactants. This is also used a Dean-Stark apparatus, which collects the water so that when the reaction is going forwards, it doesn't accidentally go backwards at the same time. Yeah.
Okay, so we also wanted to add another useful application of acetals, which is using protecting groups. So acetal formation is actually really useful because it lets you make these if you use a diol instead of two equivalents of alcohol, right? Because it's still the same thing. There are two alcohols that can attack. And then because the diol is one connected molecule, you'll end up creating a cyclic acetal. So I'm going to go through this mechanism again just because it's a little confusing to see why it's the same thing as acetal formation. This is the exact same mechanism though, it's just using a diol. So first, you protonate, and then the alcohol attacks here, flips up the pi bond, and then you need to deprotonate using the conjugate base of whatever acid you used. Remember that this only works if it's acid catalyzed because protecting groups would have to form an acetal and not a hemiacetal. So then you have this is the hemiacetal, but that's not going to do anything. So then you need to protonate the alcohol group to form this is a good leaving group, and it will just leave. And I already drew this arrow. This will attack here on the carbocation, and then the conjugate base will deprotonate, and you end up with a cyclic acetal. And this is the protecting group. So you see how there is no longer a carbonyl there. It's a protecting group. I like to think of it as kind of like putting a cover on the carbonyl. And this is really useful because, as Katie said before, this is reversible. So if you add acid and water, it'll go back to being a carbonyl. So you can have it on there for as long as you like. And while the cover is on, or the protecting group, it's not a carbonyl. So here's an example of why you might need to sometimes use a protecting group. Let's say you have this molecule. This seems like a good place where we could add some magnesium and ether to make it the Grignard reagent. But it's a special Grignard reagent because there's a carbonyl function, which we haven't seen before there being. And so let's say we want to just do a really basic reaction with the Grignard reagent and react it with an epoxide and do an epoxide opening. Well, this what we're envisioning is for this nucleophile to attack this electrophilic carbon and then open up the ring. But that won't work because if you look at the molecule again, we notice that there is a nucleophilic carbon and also an electrophilic carbon there. So it's actually going to attack there on its, like in an intramolecular reaction and do this, and it's going to form a ring. And that's not what we wanted because we wanted to use the nucleophilic carbon to attack an epoxide. So this is what we do. I'm not going to go through the whole mechanism, but we just apply what we just learned. So we use the diol and we create a protecting group there. This is the protecting group. And then we can add the magnesium and ether and we form the Grignard function that we had before, but this time it can't attack there because there's no more carbonyl carbon. And then it's going to attack the epoxide and do an epoxide ring opening, and that works. I added the carbons from the epoxide are in blue so that you can see where it added, but this is just a normal epoxide opening. And then finally, the cool thing is that the quench here, which quenches the O- into an alcohol group, also simultaneously is the reverse reaction that turns the cyclic acetal, or the protecting group, that turns the protecting group back into the carbonyl function here. And so this is what we wanted, and we ended up with it. So we are happy because we used protecting groups.